Okay, it's 7 o'clock, so let's go ahead and get started today. All right, good evening, everybody. How's everybody doing today? Doing well, I hope. Yeah, we're in the second to last week, so next week is going to be our last week lecture together. You know, we're really quickly approaching the end. Okay, so the plan for today is to continue our lecture notes on turbulence. So we have the second half of that notes to cover. Before we do that, I have a few announcements. So first announcement I want to make is that this morning I wrote the study guide for the final exam. So you can find that on Titanium. So the study guide will basically help to guide your studying. So if you read it and you compare it to the stuff that we've covered before in the past midterms, you'll see that there's elements from all the midterms, but I did take out some stuff so that you don't have to study kind of too much. So it's a lot of conceptual stuff because this class has a lot of concepts, but hopefully that study guide will be there to kind of help you guys study. Okay. And as for the format for the final exam, it's going to be the same as the last midterm. So it's going to be a take-home exam. So basically, the way it's going to work, I'm going to upload an exam onto Titanium, and you'll have 24 hours to complete it and then upload the answers back. Okay. So basically, exactly the same thing as we did before. So you can use all your notes, the lecture videos, any posted notes. The only thing is that just please don't please don't discuss it with any of the students until after the exam is done. Okay. So the next announcement I want to make is that I think maybe you guys got emails about it already, but the SOQs should be available for this semester. So those are our course evaluations. So normally we do that in class in the last week of class, but since we can't do that anymore, we're moving it to an online system. So please fill that out. For me, those evaluations are something that's really important to me because it's I'm still relatively new at this. Like this is still only my third semester teaching here, and especially for you guys, this is my first time ever teaching a graduate class here. So I know I made a lot of mistakes. I think there's a lot of things I could have done better. So just for the sake of for me that I want to be able to teach this class really well and much better in the future. I really rely on your guys' honest input to help me reach that. So please fill that out and please be honest. Tell me things that work, tell me things that could have done better. And I'll read all that and I'll take it to heart. So please fill that out as kind of as I think the due date for that I think will be next Friday. But make sure you kind of sit down and really think about how this class went for you, especially with all the virtual instruction stuff going on. I think everyone's still kind of trying to figure things out. So I think any feedback that you guys have about, ways that we can do this better is going to be really valuable for us. Okay. So there's that. And to my understanding, I think they're also going to be bugging you with very annoying emails and, very annoying messages every time you log into the portal. So just for the sake of convenience, I think probably getting it done sooner might be better than not. Okay. So the other announcement I want to make is that I think there's I think only Patrick in this class, but I think for some of you may know that I teach a class before this, and it's a class called Computational Heat Transfer. So that class is basically about developing code. So it's actually kind of very similar to my previous life as a researcher. So my plan for that class right now is for next Wednesday. I'm going to be giving just a presentation, and instead of a usual lecture, I'm going to give a presentation on some of the past work that I've done, mostly in my graduate school on kind of the research I do on computational fluid dynamics, mostly applied to blood flow. So if that's of interest to you guys and you want to watch and you're available during that time, I'll be posting the Zoom link to my 417 lecture on our Titanium page so you can log in. So it's going to start at 5:30 next Wednesday. 5:30 next Wednesday, basically a week from today. Okay. And also, if you're in Dr. Sanders' continuum mechanics class, then he's also going to be, inviting you guys to that class as well. So we're basically going to be kind of merging kind of a bunch of classes together. So You know, because of the Zoom thing, you know, usually me and Dr. Sanders, we teach at the same time at 5:30. So we thought we'd do kind of a seminar swap. So he's going to be giving it, I'm going to be giving a talk for his continuum mechanics class. And then the next day he's going to be giving a presentation for my finite elements class. So kind of taking as much advantage of this kind of Zoom feature as much as possible. And, you know, I think giving kind of a break on the last class session where it's, you know, where you guys just can kind of get to see, you know, some cool pictures, some cool videos, and maybe some cool applications to engineering that you may not have thought of before. Okay? But for us, you know, we can't change our last class session because you know, I think you guys would appreciate having a final review session. So that's still planned. So our final class session next Wednesday is going to be a review for the final. Just kind of as your last chance to kind of ask questions and to get some, you know, to kind of nail down just any topics that you might still be confused about. Okay, so are there any questions about any of that or anything in the class before we begin? Okay, so question is, when is the final? So I believe the final is going to be on Monday of finals week, but let me double check that. Actually, it's in the syllabus. Let me check the syllabus. Let's see, final exam. Final exam is on Wednesday. So final exam is going to be on Wednesday, May 13th. So what's going to happen on Wednesday, May 13th at 7 p.m. I'm going to upload the exam onto Titanium, and you'll have until 7 p.m. on Thursday, May 14th to upload the final back. Yeah, so it's going to be in the middle of finals week. Let me write that down. Okay. So I'm still going to use the same time. It's just you know, it'll be a take-home exam. Okay. All right. Any other questions before we start today? Okay. So let's pick up where we left off. So I think last time we were here, we talked about the turbulent energy cascade, and in particular Kolmogorov's -5/3 law. So we learned that, you know, in turbulent flow, you have flow structures of many different sizes, and all of them are always constantly interacting with each other and kind of transferring energy in between. Okay. More specifically, yes. Oh yeah, May 13th. Sorry. Or kind of more specifically, you know, what happens in turbulent flow is that you have kind of large eddies, or, you know, eddies or flow structures that kind of encompass the entire geometry, and those are constantly breaking down into smaller eddies, and those are constantly breaking down even more until you reach the smallest one, and that's where viscous dissipation takes place. Okay, and so today what we're going to do is we're going to learn about what's called the Reynolds equations. So these are kind of the governing equations for turbulent flow. Okay. So last time we kind of talked about just qualitatively what turbulent flow is and kind of what characteristics you can expect. Now we're going to dive into some of the equations. Okay. So this is going to be the Reynolds equations for turbulent flow. Okay. So our starting point here is, you know, we're going to use the same formulas for conservation of mass and momentum. So we're going to see Navier-Stokes. But what we're going to plug into these is something a bit different. Okay? Because remember last time we went over what's called the Reynolds decomposition, where we say that when you have turbulent flow, your total velocity, and this is true for any flow property, so we'll also do it for pressure, it's going to be the sum of two different things. Okay? So here is your mean, and here are your fluctuations. Okay. And the kind of the properties for this was that the mean is kind of constant in time. So that's kind of that kind of represents the bulk motion of your flow in your geometry. And your fluctuations represent kind of the turbulent motions, because remember the fluctuations are going to be kind of random. in terms of their direction and magnitude to a certain extent. Okay. But the property that the fluctuations have is that they're going to be they're zero in the mean. So if you average the fluctuations over time, they're going to be zero. Okay? And we call this our Reynolds decomposition. Okay. So we can have a Reynolds decomposition of the velocity. We can also have the Reynolds decomposition of the pressure. Okay. And so when I say that the fluctuations are zero in the mean, that's what I mean. Okay. So Reynolds decomposition of the pressure would look like this. So our total turbulent pressure is going to be the sum of some mean pressure plus pressure fluctuations. Okay. Okay. And so kind of like what we mentioned last time, even though turbulent flow is very chaotic and it's very disorderly, it still follows some rules. So it should still follow conservation of mass and momentum because it's still a fluid at the end of the day. Okay. So let's start to see that. Okay. So let's plug these Reynolds decompositions into conservation of mass. Okay. So in particular, we'll use the continuity equation, right? Because that was our expression for our conservation of mass. Right? So our continuity equation is going to look like this. So it's du tot dx plus dv tot dy, okay, plus dw tot dz, okay, equals 0. And so let's plug in our turbulent fluctuations. Right? Sorry, there should be an x right here. Okay, so we have d dx of u bar plus u prime plus d dy of v bar plus v prime plus d dz of w bar plus w prime. Okay. And then what we're going to do is we're going to shift some terms around and we're going to take an average of this, and then we'll see you know, what comes out of it. Okay. Any questions on this? So there was a typo earlier. So because the final exam is going to be Wednesday, May 13th, then the submittal will be due on the next day, Thursday, May 14th at 7 p.m. Yeah, so not the 15th, on the 14th. Okay. So let's go ahead and work this through. Okay. So let's separate some terms. So let's separate a term that has to do with the mean flow, and then let's separate a term that has to do with the fluctuations. Okay. Okay. So if we separate those terms, we get the following, right? So this is the continuity of the mean flow, and this is the continuity of the fluctuations. Okay. Right. So I basically just distributed the derivatives throughout, and I just rearranged some terms. Okay. And so the next thing I'm going to do is I'm going to take an average of this entire equation. Okay. Okay. And remember, our average operator is that we're just going to take a bar and just kind of apply it over the entire expression. Okay. And then since all these terms are additive, we know that adding and the averaging is just going to commute. So we can basically apply this average to each term individually. Okay. So for all the mean terms are already an average. So if you take an average of an average, you get the average back. So those terms aren't going to change. So that's going to be du bar dx plus dv bar dy plus dw bar dz, okay, plus du prime bar dx plus dv prime bar dy plus dw prime bar dz, okay, and all that's equal to 0, okay. So I basically just applied the overbar operator to everything in the expression, okay. So at this point, what we can do is we can remember that our fluctuations are going to be 0 in the mean. So if we take the average of those fluctuations, then those are going to be 0. Okay. So this term is going to be 0. This term is going to be 0, and that term is also going to be 0 there. Okay. So if we do that, then we're left with just the following. Okay. So we're left with du bar dx plus dv bar dy plus dw d bar dz, okay, and all that's equal to 0. And so what this tells us is that our mean flow is going to satisfy continuity. Okay. All right. And so we can use that to see, how our fluctuations also satisfy continuity as well. Okay. All right. Any questions on this before I turn the page? Right. So we cancel those terms because we know that our fluctuations are going to be 0 in the mean. So if we take our fluctuations and we take the average of that, or we take the overbar, that's going to be 0. Okay. So in all these terms, we have just a simple derivative. So we learned from last time that if we take the average or we take the overbar, we can exchange those operations with the derivative. So this term right here is actually the same as d dx of u prime bar, okay? Because we know that we can exchange the order of operations between averaging and taking the derivative, okay? And so since we have d dx of u prime bar, we know that that is going to be equal to 0. So we take d dx of 0 is just going to be 0. Mm-hmm. All right, any other questions on this? Okay. So since we know that the mean flow satisfies continuity, let's take that and plug it back into our original equation. Okay. Okay. And by original equation, I mean the equation that we had before we applied the average to everything. Okay. So if we do that, then we're left with the following. So we get du prime dx plus dv prime dy plus dw prime dz, not prime, okay? And all that's equal to 0, okay? And so what this tells you is that the turbulent fluctuations, even though they're totally random, right? We don't know, how they're going to be, but they still satisfy continuity, okay? So that's reassuring. So it's we don't have a pure. We know that turbulence is not just a pure being of chaos. It's a being of chaos that follows at least some rules, and we can leverage those rules to kind of help us perform some analysis. Okay. So that's continuity. So relatively straightforward. So now we're going to tackle the beast of plugging in our Reynolds decomposition into conservation of momentum. So let's go ahead and do that. Okay. So after we plug into conservation of momentum, we get the following. Okay, so I'm gonna write this in vector form. So all the velocities are going to be vectors. Okay, so we have first we have our unsteady terms. We have d dt of u vector hat or bar plus u vector prime. Okay, plus our convective term. So our convective term is going to be u vector bar plus u vector prime. And that's dot product with the gradient of u vector bar plus u vector prime, okay? So there's our nonlinear convective term, right? And all this is equal to minus 1 over rho times nabla of our pressure. So that's P bar plus P prime, okay? Plus our diffusion, our viscosity term. So we have nu Laplacian of u vector bar plus u vector prime. Okay. Right. So that's just the Navier-Stokes equations after we plugged in our Reynolds decomposition. So when we plugged in our mean flow and our fluctuations. So the only thing is I put this in vector form so that it's kind of general for you know, for all the X, Y, and Z components. Okay. And so the next step that we're going to do is we're going to distribute the convective term. So we have basically like a foil thing going on there. Okay. So if we do that, we get the following. Okay. So we have d dt of u vector bar plus u vector prime. Okay. Plus, and we have u vector bar times gradient of u vector bar. So that's the first one. Then we have u vector bar times gradient of u vector prime plus u vector prime times gradient of u vector bar plus u vector prime gradient of u vector prime. So that's our double prime term. Okay. Right. My stylus is acting up today. Right. This is equal to minus 1 over rho delta of p bar plus p prime, okay, plus nu nabla squared of u bar plus u vector prime. Okay. So all I did there was I just took the previous expression and I just foiled out the convective term. Okay. So from this term right here, we basically got four different terms. Okay. All right. And then what we're going to do from this is that we're going to, just like we did with conservation of mass, we're going to take the average of all the terms here. Okay. Right. All right. Any questions on this? Okay. So after we take the average of this entire expression, just like we saw with conservation of mass, any term that is kind of a fluctuation by itself is going to equal to 0. Okay. So for example, we had d dt of u vector prime. Okay. So after we take the average of this, then that's going to equal to 0. Okay. So we have three such terms in this in that equation. So we have the time derivative of the fluctuation, so that's going to go away. We also have the gradient of the pressure fluctuations. So after we take the gradient, that's going to go away. And we also have the viscous term. So the viscous term, it's actually a linear operator. So when we take the average of the viscous fluctuations, that's also going to go away. Okay. But the thing that won't go away are some of the convective terms. So in particular, one of them won't go away. Okay? But two of them will, because we had two convective terms that look like this. Okay, so we had u vector bar times gradient of u vector prime, and also u vector prime times gradient of u vector bar. Okay. And so just like everything else, we're going to take the average of it. So we're going to apply the overbar operator to both of these. Okay. So normally, remember what we said before, when you take the average of two things multiplied by each other, you can't just distribute that average across both. But in this special case, because the average is already kind of averaged, that kind of acts like a constant. Okay. Okay. And so what's going to happen is that because the terms that are already overbarred are going to be average, we can apply this average operator directly to the fluctuation terms. Okay. And then since we can do that, these terms are just going to cancel out because we're just taking the average of a fluctuation, which remember is going to be 0. Okay. So after we do all of that, we're left with the following expression, which is not nearly as scary, but it's an expression that is actually gives nightmares to everyone that studies turbulence. Okay. So the first two terms are pretty normal. So we have the unsteady term of our mean flow plus the convective term in our mean flow. Okay. Plus okay. So we have this additional term right here because we have two fluctuations multiplied by each other, and we take the average of that. But since neither of them are constants, we have to kind of respect that kind of average on top. So we can't really do anything with this term right now. So we're just going to leave it as is. Okay. Next, we have our pressure term. It's pretty standard. And then we also have our viscous term. Okay. So most of everything here looks standard. The only guy who wasn't really invited to the party was this guy. So it's a kind of a product of two turbulent fluctuations with the gradient operator in between with an average on top. Okay. So this term has a very special name. So this term is called the Reynolds stresses. Okay. If you're getting tired of Reynolds, that's okay. Reynolds basically put his name on everything fluid mechanics. You can't really escape him if you're doing any kind of fluid mechanics. Okay. So the reason it's called the stresses is that it actually has a very similar function to the viscous stresses. So we'll see later on that this Reynolds stresses will actually be able to transport momentum. Okay. But to put it in more standard, these actually have a more standard form. So the way it is right now, it's perfectly valid. But we actually put this in another form, just kind of for a lot of turbulent equations. Okay. So the other form for this, and the reason I didn't have this at first is because we're introducing kind of a new mathematical operator. Okay. So the kind of the standard form that people use for the Reynolds stresses is this right here. So we take the divergence, so we have nabla dot, so that's not new. And then we have u delta u vector prime, and then we have this new symbol right here, which is an x surrounded by a circle. So this this operation here is called an outer product, right? And so you can kind of think of it as kind of the opposite of a dot product, because the dot product, remember, you take two vector quantities. Here you have two vectors, and you dot product them, you get a scalar. So you kind of go one down in the number of dimensions. But for an outer product, you do the opposite. So for an outer product, you go kind of one dimension up. So you take the outer product between two vectors. What you're going to get is a tensor or a matrix out of this. Okay. And so the reason why it's called stress is hopefully starts to make a bit more sense, because it's just like the viscous stresses. Remember, the viscous stresses is the viscosity times the gradient of velocity. And we know the gradient of velocity is going to be a tensor. So if this Reynolds stress is also going to be a stress, then it has to be a tensor. And the way that we get that tensor is we use this kind of outer product operation. Okay. All right, any questions on this? Okay. Okay, so if we put that all together, then we get the following equation, okay, for conservation of momentum. Okay. So first we have our unsteady term. We have our unsteady term and also our convective term. And I'm trying to draw a bar over the unsteady term, but my stylus is not cooperating. There we go. Okay. So we have that term. Okay. And this is equal to our pressure term. Okay. Plus our viscous term. Okay. And then we're going to subtract our Reynolds stresses. Okay. And remember, we take the overbar over everything. Okay. So I move the Reynolds stresses to the other side of the equation just because that's where kind of the all the stresses are. Because remember, the pressure is a normal stress. The viscous term is a shear stress, and the Reynolds stress, because it's a stress, we kind of put it together with the rest of its stress buddies. Okay? And so this equation right here has a special name. So this is known as the Reynolds averaged Navier-Stokes equation. Okay. Or in other words, you know, a term that you'll hear a lot in turbulence literature is RANS. So this is what's known as the RANS equation. So RANS stands for Reynolds average Navier-Stokes, and it's literally, you know, the name kind of tells you what it is. First, we plugged in the Reynolds decomposition into Navier-Stokes, and then we took the average, and then this is what we get. Okay? So it's the same as our standard Navier-Stokes. The only thing we have extra is this Reynolds stress. Okay, so let's talk about the Reynolds stress a bit more, because that's something that's important for turbulent flow. Okay. So the Reynolds stress, just like the viscous stress and the normal pressure, this is a stress that's going to apply an effective force on the mean flow. okay? And so just like pressure and viscous stresses, this Reynolds stress, it can modify the mean flow, right? And so how does it do that? Okay. So let me draw a profile here. So say that this is like your velocity profile, okay? So say this is our kind of our mean velocity profile u of y, right? And so, from this profile, we can kind of deduce that at the bottom here, we have a solid surface and it's stationary. And so because of the no slip boundary condition, we know that the velocity has to stop at that solid boundary, okay? And if you remember from when we did laminar unsteady flow, right? We know that the viscosity, it plays a role of basically transporting the momentum through the fluid, okay? And so what's happening here is that the momentum of the wall is kind of diffusing up through the fluid due to viscosity. Okay. Right. So the Reynolds stresses actually transport momentum in kind of the same way. So that's kind of how I want you to think about the Reynolds stresses. It's kind of a way for it's a different mechanism for momentum to transfer in turbulent flow. Okay, because remember in turbulent flow you have all these kind of random fluctuations. So if you kind of draw a particle right here, even though the mean flow is just going like steadily from left to right horizontally, this fluctuation doesn't really care about that. So it's just going to do with it whatever the heck it wants. So let's say that this turbulent velocity, this turbulent particle is going to go up like this, basically cutting across 5 lanes on the 405, making everybody angry, right? And so that's not the only one that's like that. So we're going to have other particles that do the same. So we might have something like this. Okay, it's going to be just pure chaos. Okay. So when those particles kind of change layers in this expression here, what it's going to take with it is actually its momentum, right? So let's take this particle that starts right here, okay? So right here, right, when this particle kind of moves from this lower area to the top, right, what it's doing is it's going from an area of relatively low momentum because the mean velocity here is low. And then when you go up top right here, it's going to an area of high momentum, okay? So, that particle is also going to take some of this momentum with it. So once this particle kind of joins this new neighborhood up here, it's basically going to slow everything down up there because, it's coming from a place with not much momentum and is kind of basically going to be pulling everything back, okay? So this particle, just by the fact that there's some turbulent fluctuations and it can kind of jump different layers where it normally can't in the mean flow, it's going to transport some momentum in kind of this exact same way that viscosity does. Okay? And this kind of phenomenon of kind of these fluctuations kind of transporting stuff in between different layers of the fluid, it has kind of a special name. So the name is called, the general name is mixing, but kind of the more precise name for this is called macroscopic mixing. Okay. Right. So if you've taken heat transfer before, you know that if you have a turbulent flow and you have kind of these chaotic flow structures, you know that turbulent flows will transport and convect heat a lot better than laminar flow because you have these fluctuations that can jump layers. Okay. So just like how turbulent flows can transport heat and mass a lot more easily, it can also transport momentum as well. And that mechanism or that way for these Reynolds stress to transport momentum is encapsulated in this term right here in the Reynolds stress. So physically, that's what these Reynolds stresses represent. It's a way for these turbulent fluctuations to transport momentum just by the fact that it can kind of jump wherever it wants and take its momentum kind of with it. Okay. All right, any questions on this? Okay. Okay, So now that we've established that the Reynolds stress can affect momentum, just like viscous stresses and pressure, how does it compare to all these things? So in general, for turbulent flows, the Reynolds stresses are going to be much, much higher than viscous stresses. Okay. And that kind of makes sense a little bit because remember, for turbulent flow, we have a Reynolds number that's really high, and we know for a Reynolds number that's really high, then viscous effects relatively low, right? So for turbulent flow, where you have these, turbulent fluctuations, they kind of really diminish the effect of viscosity, and that's kind of consistent with, what we know or what we've learned from before. Okay. All right. So the other thing about the Reynolds stress tensor is that it's symmetric. Okay. So it follows the same kind of properties as the velocity gradient, where if you kind of go across the diagonal, they're going to look the same. Okay. Right. Right. So then, that's why Reynolds stress is always on the other side of the equation because it's a stress, right? So now we have this kind of very nice Reynolds average Navier-Stokes. We have our Rand's equations. So the question now becomes, how do we solve this guy? Okay. So the unfortunate thing is this is kind of where we have to stop because solving the Rand's equations, even though it looks fairly innocent, it's just Navier-Stokes with one additional term. That additional term causes all kinds of complications. Okay, so let me kind of just give it to you just straight. Okay, so normally when we solve our conservation of mass and momentum, we have four equations, right? So we have one equation for conservation of mass, and then we have momentum for x, y, and z. Okay, so in theory, just just purely from algebraic considerations, we should be able to solve for four different unknowns. Okay. Okay. And so our four unknowns are going to be our three components of velocity and the pressure. Okay. So this will be U, V, W, and P. Okay. Okay. Right. And so for turbulent flow, if you count Rand as basically the conservation of momentum, we still have the same four equations. So we have conservation of mass and conservation of momentum in each of the four or each of the three coordinate directions. So we have four equations. Okay. The problem now is that we have more than four unknowns because we have not only the mean components of the velocity, but we also have the fluctuations. Okay. So actually we have fluctuations in both the velocities and the pressure. So we have 8 unknowns. So we have U bar, V bar, W bar, P bar, and we also have all of their fluctuations. Okay. So we have 8 unknowns and only 4 equations. So there's actually no way to solve this. Okay. So this is a conundrum for sure, and it's such a conundrum. It has a special name. So the name for this conundrum is known as the closure problem of turbulence. Okay. So the reason it's called that is because as opposed to our laminar case where our set of equations are closed, where we can solve, in theory, solve for every unknown using all the equations. In turbulent flow, it's impossible just because we have way more unknowns than we have equations. So our equation set isn't closed. And so a lot of turbulence research is kind of centered around this closure problem of, how do we actually close this this system? Okay, so as you can imagine, they add additional equations to this, and the methods for doing so is known as turbulence modeling. Okay. So a lot of turbulence modeling, they rely on things like experimental data. They rely on dimensional considerations. They rely on a lot of other things. So people have been trying to find, the kind of the best turbulence model for, many years now. So no one's found one that's kind of the no one's found the unicorn yet. So there's a lot of good ones out there that work well in certain situations, but no one's found the one that kind of works in total. So we'll save the discussion of turbulence modeling. So that's what we're going to do on next Monday. So it's, as you can imagine, it's a field that goes really deep, but we're just kind of scratch the surface and kind of, just go into some of the thought processes that go behind turbulence modeling. Because, for practicality's sake, a lot of you who are going to be working with turbulent flows in practice will probably use some kind of CFD code. So when you're using a CFD code with turbulent flow, you often need to select, what's going to be your turbulence model. So we'll talk about, one primary one, at least the one that makes the most physical intuitive sense, and we'll kind of briefly talk about some of the other ones. But that'll be next week. Okay. All right. Any questions on this? Okay. Okay, so the last thing I want to cover this week is kind of an application of turbulence, and I kind of picked this one just because it's kind of related to a lot of the other flows that we've covered in this class. So this class is based on viscous flow, and we know that viscous flow kind of happens when you have flow that's kind of confined to a small gap, right? So we saw that with lubrication theorem or lubrication theory, kind of head on, but then a lot of the other problems that we solved before also kind of followed this trend. So the study of turbulent flow that's kind of bounded by kind of solid walls kind of has its own set of theories. So that's what we're going to do. So we're going to cover what's called wall-bounded turbulent shear flow. Okay. So this is important just because a lot of engineering applications, they involve turbulent flow in a pipe or turbulent flow in a small duct, right? So you're going to need to be able to take turbulence into account once you're working with these kinds of devices. Okay. So these kinds of flows are a bit different from kind of the general turbulent flows that we've been discussing before, because you have the presence of that solid wall. Okay. And what that solid wall boundary is going to do, it's going to kind of suppress some of the effects of the turbulent fluctuations. Okay. And the reason for that is, remember, fluctuations are kind of random, kind of directions that the velocity can go. But no matter how random it is, the velocity can't penetrate through a solid wall. Okay. So what tends to happen is that if you have a solid wall like this, right, and you have turbulent fluctuations, so you have this particle, it can kind of go up here. But if that particle tried to go into the wall, it can't do that because the wall says no. right? And so what kind of the net effect of that is that if you consider kind of the relative strength or the amount of fluctuations that occur, and you do that, you compare that to fluid that's kind of next to the wall, and you compare that to fluid that's kind of far away from the wall will, near the wall will have a lot less fluctuations. Okay. Okay. And so if you have much less fluctuations, we know that the Reynolds stresses in comparison will also be less. And if the Reynolds stresses are less, that lets viscous forces come, to be more dominant. Okay. But it never gets to such degree that that we get a laminar situation. So the fluctuations will still be there. It's just that their effects will be a lot less compared to regions that are outside the wall. Okay. So what happens in these kind of wall-bounded turbulent flows is that you kind of have an interaction between viscous stresses and also the turbulent Reynolds stresses. Okay. Right. So let's kind of qualitatively kind of talk about some of the results. Okay. So if you look at kind of flow in a pipe, okay, or it can be flow in a square channel, okay. So we've solved this problem kind of many times before. So we know that if you have laminar flow, you get a very nice kind of parabolic velocity profile. Okay. And so if you have turbulent flow, what tends to happen is that because you have the interaction of turbulent stresses and also viscous stresses, that the turbulent Reynolds stresses are going to want to transport momentum faster than the viscous ones, right? And so what tends to happen is that you end up with a profile where near the wall you have much sharper gradients. Okay. But then once you get to the middle of the flow, then that velocity profile tends to level out. Okay. Okay. And so the term that people use to describe turbulent velocity profiles is that they look more blunt than laminar flow. Okay. Okay. Right. And so what we're going to cover right now is that we're gonna talk about kind of the evolution of the velocity as it goes from the wall out into the center of the fluid. Okay. Any questions on this? Okay. Okay. So it turns out it's the situation is a bit complicated. So even though I drew it kind of as one curve going from the wall up to the middle, the way that people have kind of described this is that there's kind of distinct regions. So as you kind of go away from the wall, you go from kind of one region to the next, and each region kind of has its own kind of behavior. Okay. So first, let's go. Or let me draw them out first. Okay. So if we draw the wall that looks like this, okay. So we'll go over 3 regions here. Okay. So the first region we'll cover is known as the viscous sublayer. Okay. So this is the region that's kind of right next to the wall. So the region is called the viscous sublayers because since you're right next to the wall, the velocity fluctuations there are almost zero. Okay. So in this is kind of the only region in turbulent flow where the viscous forces are going to dominate. Okay. And the reason it's called a sublayer is that the thickness of this layer is extremely thin. So you're talking about, it's so thin that the stress is basically going to be constant in this sublayer. Okay? And that's going to be important when we go over the equations later. Okay? Okay. So the next layer that we have is known as the buffer layer. Okay. And so in the buffer layer, since we're getting a little bit farther away from the wall, the fluctuations are going to be a little bit more prominent. So the buffer layer is going to have kind of pronounced, turbulent effects, but still viscosity is still relatively important. Okay. And then the last layer that we'll cover is, or actually the first one that we'll cover after this is known as the logarithmic layer. Okay. And the reason it has that name will be kind of explained very shortly. Okay. But these are kind of the three different layers that you have in wall-bounded turbulent flow. Okay. So first, let's go over the logarithmic layer. Okay. So the logarithmic layer is defined, are the velocities in this layer. Okay. Okay. So the velocities in this layer follow a very special formula. So it's called the law of the wall. Okay. I don't know who came up with that name, but it's catchy. Okay. But it's not nearly as exciting as the name makes it sound. Okay. So basically what it says is that the velocity in this layer, it depends on some kind of logarithm. Okay? And so what we have in this layer is that we have u plus, and I'll explain what the plus means in a bit. Okay. So we have u plus is equal to 1 over kappa times the logarithm of y plus c. So this here's our law of the wall. So it's a relatively simple formula, but we kind of need to define all of these constants because basically none of these we've seen before. Right? So we have u plus, y plus, kappa, and c. Okay? So let's go over kappa and c first. So kappa and c are going to be just constants, and their values have been kind of experimentally determined. Okay. So you have a kind of a table here. Okay. So we have three different kind of characteristic wall-bounded turbulent flows. So we know what channel flow is. So channel flow is just a flow in kind of a rectangular channel. Pipe flow is obvious because that's going to be flow in a cylindrical pipe. And then BL down there stands for boundary layers. Okay. So those are kind of the main three situations where you have turbulent flow with a solid boundary. Okay. And so through experiments, people have found the values of these constants. So this is going to be 0.37. This is going to be 3.7. Okay, for channel flow. So that's those are the constants you would use for a rectangular duct. Okay, so for a pipe flow, this is 0.41. This is 5.0. Okay, and then for boundary layers, this will be 0.384 and also 4.17. Okay. So if you're going to use the law of the wall to determine velocities for wall-bounded turbulent flow, these are the constants that you would use depending on what kind of situation that you would have. Okay. All right. Any questions on this? Okay. So now let's go over U plus and Y plus. So U plus and Y plus, these are dimensionless velocities and dimensionless distances. Okay, and so their equations are given by the following. So U plus is given by U, which is our standard velocity, divided by UT. Okay, so UT is another constant that we have, is another value parameter that we have to go over. Okay, so this the name for this is going to be the friction velocity. Okay, and so the friction velocity is it's a measure of it's kind of a scale for the velocity based on the wall shear stress. Okay, so we'll see that in a second. Okay, so this is our formula for Y plus. Okay, our U plus. Next we have our formula for Y plus. Okay, so this is equal to Y. Again, we have our friction velocity divided by the viscosity. Okay. So U and Y here are kind of the physical velocities and physical distances that we've known. Okay. Okay. And so UT, that's our friction velocity. The way that we compute it is we take the wall shear stress and then we divide it by rho. Okay. So this is wall shear stress. And this right here is density. Okay. And so the way that you can compute wall shear stress is given by this formula here. Okay. So we have 1/2 times rho U squared CF. Okay. Where the CF right here, this is the friction coefficient. Feels like we're playing whack-a-mole. So every time we write an equation, we introduce a new unknown. So we need a new equation, but that has a new unknown. And then, so, you know, we keep kind of whacking them down like that. But we're almost done, I promise. Okay. Because now we just need equations for the friction coefficient. Before we do that, are there any questions on these formulas here? Okay. So then the formulas for the friction coefficients are given by the following. So there's two options here. Okay. The first option is you can do 0.37 times log base 10 of the Reynolds number with respect to x. Okay. And this is raised to the minus 2.584. Okay. So those aren't magic numbers there. So obviously this is something that's been determined by experiments, right? And some and a lot of numerical fitting. Okay. Okay. And so the other option that you have for CF is you can do 0.445 divided by ln of 0.06 times the Reynolds number with respect to x, okay, squared, right? So again, that's also an empirical correlation. So both of these work, okay? I think they have slightly different origins because they were kind of based on maybe a different set of experiments, but I think they both kind of have the same relative agreement. Okay. So remember this, these sets of equations here were used to determine the velocity in the logarithmic layer, right? And the reason, remember, the reason it's called the logarithmic layer is because we have the law of the wall, which says that the relationship between velocity and distance, you have this kind of logarithmic expression. Okay. So next, let's go back to the bottom. So let's go back to the viscous sublayer. Okay. So remember, in the viscous sublayer, we're basically right next to the wall. So we're basically just a very small region away. And so because we're so close to the wall, the fluctuations don't really reach down there because of fluctuation. Any fluctuation knows that if it goes down to the wall, it's just going to be turned away. So the effect of turbulent fluctuations is really small here, although it's still present a little bit. Okay. Okay. And so because the Reynolds stresses are very small there, here the viscous stress is going to dominate. Okay. But this region where the turbulent fluctuations are almost zero, it's a very, very unique spot. So this layer is extremely thin, and so because this layer is so thin, the stresses are basically going to be constant in this region, and in particular, those stresses are going to be equal to the wall shear stresses. Okay. Okay. All right. Any questions on this? Okay. So how thin is thin, right? So I keep saying that this layer is really thin, but let's put some numbers on it. Okay. Sort of. So generally, when experiments were run and they tried to find the width of this layer, they found that the viscous sublayer was about a length of about 5 units of y plus. So if y plus is less than 5, okay, then this tells you that you're going to be in the viscous sublayer. All right. So in the viscous sublayer, the equations look like this. Okay. So the stress, which I said is going to be constant in this viscous sublayer, has this following equation. Okay. Okay. And so since the turbulent fluctuations are so small here, we can kind of roughly ignore their presence. So the only stresses that we actually get are strictly the viscous forces that appear from the mean flow. Okay. And so if you solve for u bar here, okay, this is going to be equal to tau y all over the viscosity, okay? And then the velocity distribution inside here, if you want to go by u plus, is that you have this linear relationship where u plus is just equal to y plus, right? So once it looks kind of weird because we have a velocity that looks like a distance, but remember both of these are dimensionless, right? The value for the dimensionless velocity actually equals the same as the dimensionless distance because our turbulent effects are going to be really small here. So that's the viscous sublayer, right? So kind of a strange layer, in the context of turbulence, because the turbulence effects can be really small, right? So the next we have the buffer layer. So the buffer layer, it gets its name because it's kind of the buffer in between the viscous sublayer and the logarithmic layer. And so because of that, you have really complicated physics going on, right? So kind of viscous effects and turbulent effects, they're both kind of acting with relatively equal importance. Okay. And so because of that, the velocity distribution in the buffer layer, it doesn't really follow the law of the wall, nor does it follow this viscous sublayer. Researchers are still trying to find a good expression for this, but we know for sure that in the buffer layer, u plus does not equal y plus, okay? So it's not a viscous sublayer. And it's also not a logarithmic layer, okay? So both of these expressions aren't true, okay? So it kind of does something different. So researchers are still trying to find out. And the width of the buffer layer is given by this. So if y plus is between 5 and 30, then you're in that buffer layer where turbulent effects are getting stronger and viscous effects are getting weaker. But because you kind of have this rapid transition between the two, it's kind of hard to characterize the velocity here. Okay, any questions on this? Okay. So let's summarize kind of the widths of all the different regions. Okay, so first we have the viscous sublayer. Okay, so we know that this is relevant for y plus is less than 5. The buffer layer is valid for y plus between 5 and 30. Okay, and the logarithmic layer is valid for a much bigger range. So if you're between 30 and roughly 500, I think there's some debate on what that exact number is. You're going to follow the law of the wall. Okay, and so you might see a plot that looks like this. Okay, where you have up here you have u plus, and down here you have y plus. Okay, so if you make a plot for those two, what you have here, and this is a logarithmic plot, so you have 10 to the minus 1, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, okay? And so what you should see is that up until about 5, right here, you have kind of a viscous sublayer, okay? So it's not a straight line because remember the x-axis is logarithmic, okay? Okay, you have another region for the buffer layer, so it kind of looks something like this, okay, where that goes up to 30. And then in the logarithmic layer, because the velocity distribution is logarithmic, and we have a semi-log plot here, then you have kind of a straight line. And so there's been a ton of experiments done that kind of confirms this, this distribution here. All right, any final questions on this? Okay, so there's no more questions. We're out of time for today. So thanks for tuning in as usual, guys. So have a great weekend. Please stay safe and please stay healthy, and I'll see you guys on Monday. Yep, thanks everybody.
Thank you.
Mhm. Okay, I'm going to end the meeting.